All right, this is it. The last lesson of this unit, the most important lesson of this unit, one of the more important lessons of the entire year. Doesn't mean it's hard, it just means it's really important, okay? So we started talking about areas under curves. Sometimes they were straight lines, like this function 2 from 1 to 4. You could find the area under that curve, okay? We talked about that. We talked about how, if we have non-straight lines, we could approximate. And we talked about antiderivatives. And what we noticed last class is that we're using this integral for both situations. And why are we using this integral? You could probably assume they have something to do with each other, areas and antiderivatives. Well, you would be correct. Okay, they are related. Now, the connection between these two will reveal itself after you figure out this word problem. Okay, here we go. You guys write down the two ways, using the information that I provided, that you can use to calculate how far I've traveled. And the connection is in that there are two ways to do this. Okay, what's one way to find out how far I traveled? Sure. I started at the mile marker of 234, and I finished at the mile marker at 374. If I take my finishing position and I subtract my initial position, I'll have my distance traveled, so long as I'm not going back and forth in between. Okay? And this is 140. Okay. So that's one way. What's the other way? Yeah, distance is equal to your velocity times your time. Sure. I drove 70 miles per hour for 2 hours. I drove 140 miles. Okay? Well, let's look at least this guy on the left graphically. Okay? Let's examine this if I gave you the graph of velocity with the y-axis and time on the x-axis. Okay? Where would this 140 appear graphically? Ha! Okay, this 140 is actually this area here. Well, so that means I can say that the area from 0 to 2 under my velocity curve was at 140. Well, areas under curves can also be calculated by taking something else and using something else to find that area. So this area I also could have found by taking this finishing, or this position at time 2 after 2 hours. I'll say the position at time 2. and subtracting my position at time 0. Well, what's the relationship between velocity and position? If I take the derivative of position, I get velocity, right? If I take the antiderivative of velocity, I get position. Do we see the connection now? The area under the curve is not the antiderivative, but the change in my antiderivative over the interval. Okay? So, maybe that's like, that's not, like, what are you talking about? This is just base times height. Why would I need to connect it here? I can just do 70 times 2. Well, what if I couldn't get away from you fast enough? So I decided to jump onto a rocket-propelled car because I could. And the rocket-propelled car traveled at a velocity that is equal to 3t squared. So my velocity was increasing and I was accelerating, always. Okay? Assume I started at mile marker 0. Could you tell me how far I traveled between the first second and the 5th second? Well, graphically, what is this distance that I traveled? The area, right? So whatever this is, that's my distance. Well, can we do base times height to find this? No, it's a curve. This is a lot different. I could use a Riemann sum to approximate it, but I want to know exactly how much area is in here. I need to find this area. Well, instead of worrying about my velocity, instead, let's just figure out where I was at second number 1, and let's figure out where I was at second number 5, and if I subtract those two positions, boom, that change in the position gives me my total distance, which gives me my area under my curve. So let's start by first taking the antiderivative of 3t squared. What's that equal? T cubed plus a c. Now the c is very interesting. This is considered like my starting position. I was told that I started at mile marker 0, so right now for this example, I can say c is equal to 0. Okay? So all of a sudden, my position function is t cubed. Well, instead of worrying about trying to calculate this geometrically, because I can't, instead, all I have to worry about is the position I was located at time 5 and the position I was located at time 1. And by subtracting those two values, boom, I get the change in my position, which is the distance, which is the area. The area under the curve 3t squared between 1 and 5 is 124 units squared. In this question, this would be feet. Okay? So that's the beautiful connection. Antiderivatives can help us give us the change, or the change in an antiderivative can help us get the area under a function. And that is, my friends, the fundamental theorem of calculus. They think it's so important, they called it the fundamental theorem of calculus. That the area under a curve from A to B can be calculated by finding the antiderivative of the function and finding the change of that antiderivative between A and B. Area under a function is equal to the change of its antiderivative. On that interval. Okay. Now, I'll show you kind of the steps to do this.
Hey, I'll just look in here.
Yeah, grab it. You're cool. Later, Mr. Conwell. That's little Mr. Conwell. Anybody knows the older Mr. Conwell? That's little Mr. Conwell. He sits in the exact same seat as his brother. I teach him algebra. It's funny. So, it's pretty rad, yeah. Dude likes his books. It's cool. All right. So, if I want to find the area under the derivative, if I want to find the area under f prime, well, what I'm going to do is first find the antiderivative. Okay? So, I'll find the antiderivative, which will be this f. And let's say I include this c. Because usually when you find the antiderivatives, you have this c. I will find the change in this antiderivative from A to B. We'll use this line to show this step. Now, watch what happens. If I plug in b of f of b plus c, and if I subtract a, that's f of a plus c, and I'm subtracting the entire thing. What happens to c? Yeah, the c's actually go away. What that tells you is that I don't care where I start. I don't care what c is. I just care about how much it changed in this interval. Okay? This is just the change. It doesn't matter if you start at position 5 and go to position 15. That's a distance of 10. That's the same as starting at position 0 and going to position 10. Still a distance of 10. Or starting at 10 and going to 20. Whatever this constant is that would shift things up or down, it doesn't matter. We just want the change in f of b minus f of a. Okay? So the c doesn't matter. What we're going to do here is kind of connect what we already know how to do with this fundamental theorem of calculus to show you that this works. Okay? So this is the example that I showed at the beginning of the class, the integral from 1 to 4 of 2 dx. I can calculate this area no problem. But I want you to see how this other way to calculate this area also works, this fundamental theorem of calculus method. So we know the area is supposed to be a 3 by 2, supposed to equal 6. Okay, good. Using the fundamental theorem of calculus, this is what I would do. The integral from 1 to 4, or the area from 1 to 4 under 2, would be equal to the antiderivative, which is 2x, or it would be the change of the antiderivative. The antiderivative is 2x plus c, but we just talked about how we don't need the c if we're talking about the change, so I'll just exclude it, between 1 and 4. Well, to find the change, it's just your antiderivative at b minus your antiderivative at a. That'd be 2 times 4 minus 2 times 1. 8 minus 2, 6. This area, calculated geometrically, is equal to the change in its antiderivative. Okay? So that's how we work this. Your turn. I want you guys to find the area under this line, 1/2 x plus 2, by first using the fundamental theorem of calculus and finding the change in its antiderivative. And then I want you to go back and confirm that that area that you found is correct by using geometry and figuring out this area of this trapezoid. Okay? Work through it. Check your answers with a neighbor. Help each other out, especially with the fundamental theorem of calculus thing, which is the new thing. And then make sure you go back and confirm. Now, it's important when you're subtracting f of a, you subtract the entire f of a. In this situation, it's no big deal because it's 0, but it's something to definitely be careful of. (36 divided by 4 is 9. 2 times 6 is 12. Then I have to subtract a big 0. This is 21. So I think the area under this curve is 21. This is in units squared. So we're not really told what these units are. Well, this area, let's see, would be 1/2 the base length, which is the height, which is 6, times the first base plus the second base. That's 2 plus 5. Let's see. That's 3 times 7. Voila! We did it. Okay? Areas under curves equal change in antiderivatives. Thought of in terms of distance equals rate times time, and the position in the future minus your position now. All right, one more. Well, not really one more, but here's another one. The area under x squared between 0 and 2. Once straight lines go away, this becomes our only way to find exact areas under curves, which is great. Just the change in my antiderivative. Okay, I feel okay about that answer 8/3, but I kind of want to be able to check it and make sure that is a feasible answer. Because, like, I don't know, this picture might not be perfect. You know, I don't know if 8/3 is correct. What can I do to, like, make sure that that is a reasonable answer? Perfect, Miss Coffee. We could do a Riemann sum to see what approximations of this area would be. Let's do a left Riemann sum. Yeah. 0.5, 1, 1.5. A left Riemann sum would be under or over my actual area? Under. Okay, let's see. We'd have a 0, and then we'd have a 0.25, and then we'd have a 1, and then a 2.25. So it would be 0.5, which is the width, 0.25 plus 1 plus 2.25. What does that equal to? So that's 2.5 plus 1. That's 3.5 times 0.5. What's 3.5 times a half? 1.75. Okay. So what's 8/3? 2.6. Okay, well, it's under. It's not a little bit under. Let's do a right Riemann sum. Right Riemann sum is going to be over, right? So 0.5, I'll have 0.25, 1, 2.25, and 4. What do I get there? $3.75. Okay, well, that's over. Well, that makes me feel a little bit better that 2.6 repeated is my answer. What would give me a pretty accurate approximation? Yeah, let's do a trapezoid. Let's do a trapezoid. So, 1/2, my consistent widths, my first plus my last plus double my middle. See what that gives me. 0.5 times 0.5 times 4 plus 2 times 0.25 plus 1 plus 2.25. 2.75. Yeah, that looks good. This is good. This definitely looks good. And the trapezoidal Riemann sum we could see would just be a little bit over since this graph is concave up. So, check. All right? We did it. Well, I don't even need to give you a graph. You don't even need a graph to find the areas between a function and the x-axis. You just need your knowledge of antiderivatives. Area under a function is equal to the change of its antiderivative. You don't need the plus c's. Make sure when you subtract f of a, you are subtracting all of f of a, and the other ones we don't really worry about it because there's 0. In this case, we do. So let's see. This is 9. This is negative 8/3. This is 18/3. Negative 10/3 plus 8/3, negative 2/3. Units squared. That's my area. Find it for the next one. And let's change this up a little bit for sake of ease of calculations. But let's make it a little harder. Let's go from 2 to 3, but let's make this 3x squared, and this is 2x. Yeah. Check your answers with a neighbor. We should get 16 units squared. Remember, we're still finding areas, so keep that in mind. We are finding a change, and if you think about it in terms of like the change in x's, this could be considered units in terms of, you know, a y coordinate minus a y coordinate, that's units. But we now have a connection between this change in these y coordinates and an area, so we can almost label this 2 different ways, depending on how you want to think about it, which is kind of crazy if you think about it. A change in y's and areas the same. Okay. You see something like this? Yes, you could do this geometrically, or now you can use the fundamental theorem of calculus. Maybe you use this to check. And then I want you to do this one twice. Actually, I'll give you a different one. No, I'll give you this one twice. The antiderivative at 2 pi and at 0 would be the same thing. Yep.
No, but like 2 pi and 0 are the same spot of the graph, right?
Yes.
So it's here.
Yeah. You can confirm that. That was the whole point of the question. Look at the sine graph. Does it make sense?
No.
The area from 0 to 2 pi.
Oh, I mean, yeah. Right.
Yeah. This is -1 minus -1, which is 0. That should make sense, right? This area and this area cancel each other out. But what's really cool is this is pi right here. What is the area of just one of these humps? It's not still 0. I definitely think it's positive. Let's figure out exactly what it is. You figure it out. Tell me what this area is in units squared under this sine curve from 0 to pi. What do we get? 2. Isn't that crazy? Area under a sine curve is 2 squared units. It's like, it's too, like, works out too well, you know? Math sometimes. It's like, wow, how can you be so simple? Darn you. It should be more complicated than that. Okay, I could give you the picture, and you should be able to find the area now by setting up the integral and then using the fundamental theorem of calculus. And this is from 0 to 4. That's F. You don't need a calculator for 4 to the 3 halves, right? Okay, then let's make sure we can calculate 4 to the 3 halves. You can use your calculator to check, but let's make sure we're good with doing that by hand. Plus C, but you don't need it. Remember, you can rewrite 4 to the 3 halves as the square root of 4 cubed, or 4 cubed square rooted. Either way, you get 8. So this is 16/3 plus 8. That is 24/3. 40/3 units squared. Or just units, depending on how you think about it. Yeah, let's do that one. It's x plus sine x. X plus sine x is the sine curve, but it kind of goes on a diagonal, like that. We can find the area between x plus sine x and the x-axis from negative pi over 2 to pi. Well, that's not fun. The 4 pi squared over 8 plus 8 over 8 minus a pi squared over an 8. So that's 3 pi squared plus 8 over 8. Or 3 pi squared over 8 plus 1.
Where did that 4 come from?
I multiplied this by 4 over 4, so that it's a pi squared over 8, because I plugged in pi over 2 here and squared it. It became pi squared over 4, multiplied by 1/2 pi squared over 8. Okay, so that one's nasty. Probably won't do that with other classes. All right, well, more problems could be asked of you. I could say, hey, the area under 3x squared from 2 to some number is 12. You could figure out that number. If you think about it graphically, 3x squared, like this, between 2 and some value k, this area right here is 12. Figure out what that k is. K has to equal the cubed root of 20. Some number between 2 and 3. Cool. So it doesn't have to be that far away from 2. You could have problems where all you know are function values and you can immediately be asked the area under the derivative of whatever that function is with those values. And you can answer. You don't even need to know what the function is. You just need a couple points, and you can find the area under the derivative of that function on certain intervals. Not everywhere, just certain intervals. So I'll let you figure these out. Check with a neighbor. And then we'll finish off with like a challenge problem. What? Okay. Check with a neighbor and then see. Area under f prime is just equal to the change in its antiderivative, or the change in f between 1 and 3. Now, order matters, and we haven't done anything from right to left, and we probably could have confirmed the whole areas using the fundamental theorem of calculus from right to left. It's always f of b minus f of a. If this is b and this is a, this is equal to f of b minus f of a. So in this case, I have to do f of 2 minus f of 3. Since we're going from left to right. F of 2 is 2, minus f of 3 is 4. That's 6. Okay? Units are units squared. All right. 2 challenges problems. Let's do this one first. And you don't have to worry about these f prime values. They're there to trick you. All you need is the f values, I'll tell you that. See if we can get this one. I believe the answer is 7. Anybody? Okay, all right, okay. Good. How do we do this? Well, 3, that's a function. If you're adding or subtracting functions together, you'd have to take the antiderivative of each of these. Well, guess what? This would be 3x. The antiderivative of negative 2 f prime Well, that constant times this f prime, the antiderivative would just be the constant times the antiderivative. Now, this would have to be evaluated between 1 and 4. Well, the entire thing would have to be evaluated between 1 and 4. You'd have to find the change in this. So you start with 4. And then you'll subtract that thing at 1. Notice, and you'll see these problems on AP tests and on your quizzes and stuff. They gave us f prime values, and we're not going to even use them. You know, we don't need them. They're just there to confuse us. So this is 12 minus 2 f of 4 is 6. So this is just 0. Minus 3 minus 2 f of 1 is 5. So this is 3 minus 10. So this is 0 minus negative 7. That's 7. All right, last one. Try this guy. That's to be the antiderivative of x plus the antiderivative of 3f prime. That'd be 1/2 x squared plus 3f from 0 to 3. So that'd be 9/2 plus 3 times f of 3. F of 3 is negative 4, so 9/2 plus negative 12. Minus, this would be 0 plus 3 times f of 0 is 3. So this would be minus 9. That's minus 21. So that's minus 42 halves, which is minus 33 halves. Yep. That's it. That's all I got. I'm done with some time to spare on a go time day.